In this video, we're going to take a look at how we find the moment of inertia for objects that are not simply a collection of point particles. We call them rigid extended bodies because they are extended, and rigid because if they're flexible and can bend and change shape while they're moving, that's even more complicated. So we are going to kind of look at some ideas here, right? We've got a thin spherical shell, so right, basically a ball that's hollowed out, a hoop, a solid sphere, and then a hoop spinning this way, right? Which of these has the greatest moment of inertia, right? It may not be immediately obvious when you look at them which one it is. Certainly, we know that the hoop, we talked about that in the previous video, has all of its mass rotating at a distance of r. And that is the thing we want to be thinking about. So it becomes mr squared. Every single other one of these has some of the mass that is right on the axis and therefore has a smaller effect on the moment of inertia. And so what we're going to be trying to kind of conceptually understand and then mathematically derive is what fraction of mr squared do each of these have for their moment of inertia. So B ends up being the biggest. The rest are a little bit smaller. The lowest, though, that one's a little bit harder to tell. It turns out that it's the solid sphere. And if you think about that, I hope that that makes a little bit of sense, that there's more of the mass in the middle. If A is hollow, right, and D is essentially hollow, right, most of the mass is somewhere outside. But if the solid sphere has a uniform density, then a big column of it, a core sample, a cylinder right in the middle, basically doesn't affect the moment of inertia. And that's why that one ends up being lower. These actually end up being the formulas for them. 2/3 mr squared, 2/5 mr squared, and 1/2 mr squared. More on that in a moment. You have a whole set of these. I think it's page 14 in your packet, unless that page is messed up. This came out of your textbook, but there's all these different sort of like families. There's things that basically are cylindrical, right, rotating around an axis, whether it be a hoop or all the masses at one spot, a solid cylinder or an annular cylinder, basically a hoop with thickness. And then there's things that are rotated sort of around a central axis where it's like a rod or modified rod, different things like that. So we want to be able to apply those equations. We want to extend their use with the thing we call the parallel axis theorem. And then we want to be able to derive some of them, some of the more simple ones, using calculus. That's kind of the goal. So let's start with application, right? What is the moment of inertia of a bowling ball about its center of mass? Now, a bowling ball, in spite of those holes for your fingers, is essentially a uniform density solid sphere. So we can pick that equation, which is 2/5 mr squared. Plug in our values, and we end up with about 0.023 kilogram meter squared. Now, with a new quantity like moment of inertia, it can be hard to tell, is 0.023 kilogram meter squared a big moment of inertia, a small moment of inertia? We'll hopefully get a better sense for it as we go along. And then we can take something like this. This is a composite body. It is a rod about its center plus a hoop. So if we have a rod and a hoop with the same axis of rotation, that's the only time you can really add them up together. Maybe you've glued them, nailed them, stapled them together, what happens like that. The total moment of inertia is the hoop's moment of inertia plus the rod's moment of inertia around the same pivot point or axis of rotation. So that would be an mr squared plus 1/2 m times 2r squared. Why? Because, well, the length of the rod is what goes into the 1/12 ml squared equation. That L is the length of the rod, and the length of the rod is 2 times the radius. Because they both have the same mass, the hoop and the rod, they have the same m. But if they didn't, you could just plug in the masses for each one. So in this case, it simplifies down to 4/3 mr squared. Not something you should memorize, but the process is valuable. So let's think about a ruler rotated through its center, right? You could do this pretty easily, if you were in class. I is 1/2 ml squared. The ruler is about 31 centimeters long, and its mass is 0.015 kilograms, and you end up with 1.2 times 10 to the negative 4th kilogram meters squared. We can shift the axis of rotation from the center of mass to, say, one end. And we already actually know the formula for this or can look it up, but we want to think about this idea of the parallel axis theorem. It's a relationship that tells us that if we know the moment of inertia about the center of mass of an object, we can figure out the moment of inertia around a parallel axis, right? They're both of these axes are going into and out of the page. That's why they're parallel. Using something called the parallel axis theorem. And this basically lets us use a set of moment of inertias that we either can derive or calculate pretty easily and extend them to some related situations. So here's how it works. I center of mass is the moment of inertia through the center, about the center of mass. I parallel is the moment of inertia about the axis we were trying to shift to. And we use this formula. The moment of inertia about the parallel axis is the moment of inertia about the center of mass plus mh squared. Now, m, pretty standard, is the mass of the object, but h is the distance, the perpendicular distance between the two axes. So how does that look? So if we have our hoop, the moment of inertia around the center of mass is mr squared, right? We know that. If we want to shift the axis of rotation to the rim, say we put a little pin through the thing and you let it spin kind of in a fun way, almost like using a hula hoop around your arm, we're going to use this formula. Well, oh dear, sorry. I clicked on something and got away from it. I have to edit that later. So if we want to shift the moment of inertia out to the rim, we need to think about what is this h value? Well, in this case, h is the distance between the center of the hoop and the edge of the hoop, which is just r. So we can put that all together. The moment of inertia around the center of mass is mr squared plus the mass times the shift distance of r, and then we square it. So we get 2mr squared. Right, so double the moment of inertia as if we were spinning it at the middle. And that's because now much of the mass is shifted further away from the axis of rotation. So let's look at this in a more general sense. Here's an arbitrarily shaped object, and there's the center of mass, right? You may or may not know why that would be the center of mass. It doesn't really matter. But if that is the center of mass, determined by some method, maybe hanging, maybe balancing, maybe we have a uniform density and a formula for the shape of it, who knows? But we want to shift and find the moment of inertia around P, this parallel axis, because maybe that's where we're going to stick a rod through it and let it spin. So we start and place the origin at the center of mass. We orient the x-axis, so the x-axis is perpendicular, is going directly between them, perpendicular to the axes. So now we've got the ability to measure and define where everything is. Now P has coordinates, right? H, some distance h from the original center of mass, rotation axis, and 0 in the y direction. Once we've done that, we can say, well, the moment of inertia, P, at P is, the sum of mr squared or the integral of r squared dm. But it's kind of hard to actually figure that out, right? What is this dm? How do we get there? Well, the distance of the mass from that is what we're talking about. R squared, the square of the distance from the pivot point we care about, is just x minus h for the x coordinate plus y for the y squared for the y coordinate. This is, the Pythagorean theorem again. And so we can integrate all of this with respect to dm. Of course, dm doesn't really do us any good. But what we do have is an interesting result here, that we expand it and we get x squared as a term, and then we get 2hx, and then we get h squared and y squared with respect to dm. We can rearrange this. So we get y squared plus x squared dm, right? The rest of this goes away. We can pull that out of the equation, right? That's constants times x. That stuff is the moment of inertia around the center of mass because of how that's defined. All of that distance is just from the origin. We've got the x center of mass equals 0 at the origin, right? That term goes away, and we end up with the parallel axis theorem. Now, you might be like, Mr. Grams, I didn't follow that. That's okay. It's there for you if you're interested. So let's do a sample. If you have a thin square plate being rotated around its center line, notice how I flipped it to the top view, because from the top view, it's just a rod, right? All of the mass is distributed linearly, and the axis of rotation is about the center. So we basically use a long, thin rod about the center, 1/12 ml squared, and we can end up with our answer. What if we move it a little bit over here and then let it rotate about that? Or we could also move to the edge, which would be like making a door. We can use the parallel axis theorem. We shift it a distance of 1/4 of its width or 1/4 of its length, and we end up with a new moment of inertia. And then, of course, it increases, right? Why does it increase? Because now more of the mass is further from the pivot point, the axis of rotation. So where are we? We've applied the equations. We've now started to extend them using the parallel axis theorem. And now we need to do the, well, maybe not difficult part, but the more involved part using calculus. So just to clarify, the table on page 10-2, or table 10-2 on that page in your packet, you should memorize the moment of inertia for a hoop, because it's basically the same as for a point particle. That's what you need to remember. For a disk and for a solid sphere. The reason for that is not that you won't be given them if you need them, but knowing those differences can allow you to solve a lot of problems very easily. Then you need to be able to derive the formulas for a few different cases. So why do we need calculus here? Well, we know that the mass is not all in one spot. And so we have to figure out how each little bit of mass affects the result. And we already know, just from some of the examples, that we don't end up with r center of mass squared, right? You can go back and check that. And so we can't just say, oh, well, it's like all the mass is at the center of mass, because it depends on r squared and not on r, which is what center of mass depends on. So we're going to do something we did for center of mass calculations. We're going to start with I is the integral of r squared dm, but we need to replace dm with spatial integrals, volume, surface, or line, which we've done before. We have volume density, surface density and linear density as concepts that we might need to use. So let's look at the possibilities, right? The dm is just a little bit, and in this case, it's a disk. So I'm going to use a little, shaving around, basically circular, for this one. Well, is the dm a line? Is it a volume? Is it an area multiplied by a surface density? You have to choose depending on what the shape is. And then we make a substitution, and then we do the integral. So this is just like the center of mass integration, but now the formula is a little bit different. Okay, so if we look at a rigid, rod about one end, which was the example we were looking at already, and we're letting it rotate, kind of like a door would. This is that idea. We know that it's really just a linear density this time, mass over length, which means the little bit of mass over the little bit of length is the same. We can replace dm with lambda dl, right? But in this case, we're going to deal with x as the variable here. X times lambda gives us our mass at that point. So we end up with r squared dm becoming x squared lambda dx. And we end up with the integral from 0 to L of x squared dx multiplied by lambda. Plug in the values, and we end up with ml squared over 3, which is exactly what you would find if you were to look up this formula. So 1/3 ml squared in this case. Okay. What about spinning it through its center? Now, this one we already know is 1/12 ml squared, so we can kind of try to get there. It's the same exact result. We're just changing the limits of integration, right? We're still doing the same substitution, but this time we're integrating from negative L over 2 to positive L over 2, right? Because that's how, if we call the center of mass 0, the axis of rotation 0, you end up with L cubed over 8 minus negative L cubed over 8, which means we get m over 3L, L cubed over 4, 1/12 ml squared. What about a solid cylinder, right? A solid cylinder and a flat disc are basically the same thing, um, because the length of it doesn't matter for how it's distributed radially, which is all that really matters. So we just treat it like a disc. And if we treat it like a disc, we could think of it as a surface density, mass over area, right? We're going to replace the dm with sigma dA, and mass over area comes out of that. That's what the sigma is for a uniform density object. But then this is where that thinking part comes in again. The area of this little circle that I've drawn, or circular thing, has to do with 2 pi r, its circumference, times how thick it is, which is just dr. So now we can integrate with respect to r from 0 to r, and we end up with 1/2 mr squared. And this is one of the ones that you should memorize, as well as understand how we get in terms of the integration. The last one that I want to look at is for an annular disk about a central axis. So the thickness isn't negligible, but it's basically the same as this, right? It just has a cylinder cut out of the middle. We're still going to use the surface thing because it's the same as collapsing it down along the axis. All we're really doing is changing the area, because the area is no longer the area of a circle. It's the difference between those two areas. And then the integration looks pretty much the same, right? Mass over area, we have to do something different with the area, but we don't really have to do anything different with our integration except change from 0 to r to from r1 to r2. And although the formula is a little bit complicated, it simplifies down to basically saying it's the moment of inertia of a disk of radius r squared, r2, and added to it the moment of inertia of a disk of radius r1, which is kind of an interesting result. So lots of moments of inertia, right? Different objects rotating. The moment of inertia depends on how mass is arranged, as we've talked about. And some of them are things that you should know, right? A disk, a hoop, a solid sphere. It's useful to know the rods around one end or the other. But those are ones that you could easily derive and should be prepared to derive.